Welcome viewers. We will take now the series of lectures on stereoisomerism. You know what are isomers? Isomers are the compounds having same molecular formula but different physical and chemical properties. Isomerism is of two types: structural isomerism and stereoisomerism. You are all familiar with structural isomerism. I have taken example of C4H10O. We can write these 7 isomers for this formula. 4 are alcohols, 3 are ethers. Similarly, for butene 1, butene 2 and isobutene, the molecular formula is C4H8. They are structural isomers having different arrangement of atoms. But in stereoisomerism, you have the same arrangement of structural arrangement of atoms, but have different spatial arrangement. That is, the arrangement in space differs. We will see that this butanol 2 will exist in 2 stereoisomers and butene 2 will exist as 2 isomers, stereoisomers. These will be geometrical isomers, these will be optical isomers. So we will take in detail now stereoisomerism. Stereoisomerism is of two types: optical isomerism and geometrical isomerism. We will first take optical isomerism. To understand optical isomerism, you have to understand what is this optical business. So, try to understand what is optical activity. Ordinary light propagates in waves through oscillations. Oscillations are perpendicular to the wavefront in all 360-degree direction. If you take the wave cross section of the wavefront, the oscillations may be in all these directions, in all 360-degree direction. This is ordinary light. When this ordinary light is passed through a specially designed prism called Nicol prism. Polarization takes place and the emerging light waves have oscillations parallel to each other. And this is called plane polarized light. So this is done in polarimeter. This plane polarized light, when passed through a solution of a substance, if the compound filled there rotates the plane of this polarized light, it is said to be optically active. Not all compounds do this. Only particular compounds, which you will see later, which are optical isomers, do this. They rotate the plane of this polarized light either in the clockwise direction or in anti-clockwise direction. If they rotate the plane of polarized light clockwise, they are called dextro-rotatory. Designated by a sign plus. If anti-clockwise, they are levo-rotatory. So, the extent of rotation depends upon the concentration in the solution, concentration of the compound in the solution, and the length of the path through which the light is being passed. So to have a standard value of rotation, the term specific rotation is used. It is characteristic of each optically active compound. This is originated by alpha. This is also temperature dependent, that at which temperature you have taken the values, and the wavelength of the light that you have used is equal to observed rotation in degrees upon length of the path in decimeter into concentration of the compound in gram per ml. If you take 1 decimeter long tube and 1 gram per ml concentration solution, the value obtained will be specific rotation. It may be plus or minus. Now the question arises as to what brings this optical activity in that particular compound. Why are not all compounds optically active? So, there is term chirality. It is this chirality in the molecule which brings optical activity. Chirality means asymmetry, that is not symmetric. Symmetrical molecules will never show optical activity. It is the asymmetry which is responsible for this. What is asymmetry or chirality? It is the non-superimposability of mirror images. That is, a chiral molecule will have a mirror image, and that mirror image cannot be superimposed on it. We will see by these examples. Now, organic compounds show optical activity. We have to see what type of organic compounds show this optical activity and hence the optical isomerism. One condition is there may be other criteria also. One I am telling, one condition is presence of asymmetric carbon atom in the molecule. Asymmetric carbon atom means a carbon attached C attached to 4 dissimilar substituents. If all the 4 attachments to a carbon atom are dissimilar, then that carbon will be known as asymmetric. And if such a carbon is present in the molecule, you will have optical activity in that. So the compound which we wrote isomer of alcohol, this second butyl alcohol, you see this carbon is attached to one CH3, one OH and one ethyl group. All 4 are different, one hydrogen. So this is an asymmetric carbon atom. This brings optical activity in the molecule. Now, you will ask why water molecule is not optically active or ethyl alcohol is not optically active. Water molecules are symmetric molecules and the mirror images of these are superimposable. Similarly, in ethyl alcohol, all ethyl alcohol molecules are mirror images of each other and are superimposable. When light passes through these liquids, the rotation caused by one molecule is nullified by another molecule which is mirror image of the same, and the resultant rotation is 0. But if light is passed through solutions having compounds with asymmetric carbon atom, asymmetry in it, the rotation caused by one molecule is added to the rotation caused by the other molecules because they are not mirror image of each other, and this becomes an additive property. You observe specific rotation in the molecule. Now we will take examples to show what is superimposition. I am taking a molecule first in which carbon is attached to all similar substituents. Its mirror image is this. In mirror it will be visible like this. And you will observe that if you put it on this, it superimposes. I have shown this by 4p same substituents. So this is actually ball stick model. This is carbon atom. These 2p are coming out. This p is going back, and this is in the plane. So if all 4 are similar, they are superimposable mirror images, they are identical, no isomerism in that. If you take one as different, you put one different, say Q, its mirror image will be formed like this. And this is easily superimposable. You bring it here, superimposed. It means the 2 are same, no isomerism in this, they are identical. Now I change one more. So this is the mirror image of this. See? This is the mirror image, and you can superimpose it like this. Again, there is symmetry in the molecule, and the two molecules are identical, no optical isomerism. But if you have all the four substances different, I have taken by different colors, and you see its mirror image. See, this is the mirror image. I want to show you here, then when this is asymmetric, its mirror image is this, and this cannot be superimposed. If you bring them over here, there is difference here. Or if you change this way, again there is difference. They are not superimposing. Because they cannot superimpose, it means they are two different identities, two different isomers. And these are known as enantiomers, meaning non-superimposable mirror images. One of these is dextrorotatory and the other is levorotatory. The magnitude of rotation is the same, but the values are opposite. One is plus, another is minus. So that secondary butyl alcohol, if you write like this, all the four are different. This will exist as two isomers. This is the mirror image. One is plus secondary butyl alcohol and the minus. In the next lecture, we will take other examples and how to name these two configurations.